So, as you probably know very well, the consequence of using the ionosphere-free linear combination in the classical PPP model is that the ambiguities are no longer integer values, and ambiguity resolution is still a challenging task in real-time applications. Therefore, a change in the constellation geometry is required to efficiently decorrelate the tropospheric delay, receiver clock error, and receiver height. An alternative solution is to provide tropospheric corrections from external model, high-resolution one, and if the model were good enough and reliable enough, we could fix the parameter, thus reducing the number of unknowns. While this is unfortunately not the case in real time because the models are not accurate enough, not reliable enough, we should rather provide accurate a priori model, mapping functions, and we can constrain tropospheric estimates in our equation system. The ZTD constraining approach we presented a few years ago. In this approach, we still estimate corrections to wet tropospheric delay part, but also we add additional equation to constrain these estimates. And in this case, an external information is provided from, it was provided from the near real-time solution on nearby reference stations interpolated to the user position. And in post-processing scenario, we showed that this approach improves both precision and accuracy of the height component, and it also shortens the convergence time, especially in kinematic processing. This is what you can see here. Oh, it's quite slow, sorry. So again, this approach is not suitable for real-time applications because the significant change in the troposphere delay can be observed during severe weather events. So a step towards real-time can be done using numerical weather prediction models. Forecasts are available in real time and are with good agreement with current meteorological data. It was shown by Snejderova in 2016 and Dosha in 2016 that the accuracy of ZTD in global numerical weather prediction model is several centimeters. So this is not enough to fix ZTDs in precise applications. And this is typical also that GNSS estimates are biased with respect to numerical weather prediction models. Therefore, we propose to constrain to use regional numerical weather prediction model, but to calibrate them using near real-time estimates from GNSS. And we have developed more or less in operational sense the system that is doing this in real time. We are using a near real-time system that is estimating ZTDs every 1 hour at 272 stations in Poland and surrounding areas. And we are using WRF model, which has a resolution of 4 × 4 kilometer and provides parameters at 47 vertical layers. The predictions are available 4 times a day with 1 hour resolution of parameters. How to move forward? Yeah, okay. So not only we can get ZTD in this way and in real time, because we are using forecasts, but we can also use a ray tracing technique to provide high resolution mapping functions that are consistent with the delay model. And to validate this approach, we use 3 weeks of data, which represent 3 different seasons, 3 different tropospheric conditions, namely standard, calm, and severe, all in 2015, 16, and 16, respectively. And we tested this model on 14 EPN stations in Poland. But of course, these stations were removed from the calibration process. And we performed the PPP in static and kinematic mode, and as you will see later. So the high-resolution real-time ZTD model is calculated from WRF and GNSS data using the collocation software Comedy developed at ETH Zurich. And in this approach, the collocation using the collocation coefficients of the deterministic part of the signal were estimated simultaneously from WRF and GNSS data. And in this way, one can obtain its ZTD at any point and at any time. And for the details, I refer you to the paper as below, as on the bottom. So to evaluate this, we compared the estimates from the comedy ZTD estimates that are presented here in green with a reference solution provided by EPN. So this is the final product, and in red you can see Vienna mapping functions ZTDs, and in blue you can see UNB3. And this is obvious that our combined real-time model is in a good agreement with the final products, and the sigma is 10 millimeters here. And this is, of course, because not only because of the better resolution, temporal resolution, but also because we remove the biases here. And this station Żywiec, it's in the mountainous areas, and we still observe some problems with during the rapid changes in troposphere when our model is underestimating the zenith delays. For the mapping functions, we adopted the strategy from Vienna mapping functions, in which, in this case, the mapping functions are in the form of continued fraction depending on elevation angle. And in our study, we used so-called fast approach, which is more suitable for the real-time applications, being 10 times faster than the rigorous approach. And in this approach, only the A coefficient is estimated using the slant delays and the zenith delay. Slant delay at elevation angle of 3.3 degrees. And again, we evaluated this by comparing to other mapping functions. And for the heterostatic mapping functions, we see that we see a good agreement here. But for the wet mapping functions, we see some significant differences, especially for low elevations. Here you can see it 3 degrees and 5 degrees, and these differences are getting smaller and smaller for larger elevations. Finally, to validate our approach in the positioning, we estimated, we used our own software designed for real-time processing. So in this case, we have a GPS-only solution with a classical PPP implementation, L1, L2, IONO3, float ambiguities. We used the real-time stream IGSO3, but only GPS data. And we estimated 3 types of coordinates: static coordinates, kinematic coordinates, and kinematic coordinates, but reinitialized every 3 hours. So we just reinitialized the filters. And we tested 6 different scenarios, being different combinations of a priori ZTD model and mapping functions, as you can see in the table. So in static positioning, the comedy-based variance resulted in the smallest 3D biases. So these are the 3 last bars. And the best value we get is 12.9 millimeters when mapping functions were applied consistently. So this is the solution in yellow. But unfortunately, the standard deviations here are higher by 1.5 millimeter compared to the other let's say, classical solutions. And the major difference here was observed for the up component. Here you can see the 3D results, but mainly the improvement is in the up component, or the change is in the up component, while for horizontal coordinates, the differences are very small. And I think that the gain of having much more accurate coordinates exceeds the loss of slightly worse coordinate repeatability. Of course, it depends maybe on the application. In kinematic positioning, again, we can see the significant reduction of the 3D bias. Again, this is mainly the contribution of the vertical component. But surprisingly here, the consistent application of ZTD and mapping function from the WRF did not result in the best approach. Maybe this is a recommendation for the future to use the rigorous approach. This should be still investigated. And again, we see a slight worse standard deviations for the comedy-based solutions. And finally, we investigated how our model affects the convergence of PPP solution, and here we use this kinematic reinitialized solution. And on the plots here, you can see on the left-hand side, you can see how long it takes for each solution to converge below a specific level based on the coordinate formal errors. And in the table, you can see the numbers for 10 centimeter level only. And it is, I think it is clear that the constraining ZTD estimates with the numerical weather prediction based model resulted in the shorter convergence time, and for 10 centimeters level, the improvement is here. It's more or less 13% in horizontal component and 25% in vertical component. Moreover, for this fixed 3-hour periods, we get more solution that converges at all. So not to make things longer, we have shown that it is possible to use numerical weather prediction data to calibrate them with GNSS estimates, and in this way you can get better accuracy, shorter convergence time, but with a loss of precision, slight loss of precision. Thank you.